Okay, calculus, picking up where we left off. Number 2 on page 2 was sketch the curve by eliminating the parameter and adjusting the domain. So here we're going to try to use our strategy from the second part last time, getting rid of one variable and then plugging it into the other one. Now if we look at this, sometimes it's easier to do one over the other. This says t is greater than -1. It covers our denominators here. Now x equals 1 over the square root of t plus 1 has 1t in it. This one has 2t's. It's probably going to be easier to solve for t in the x equation. So let's see. I'm going to multiply the square root of t plus 1 over to the other side and divide by x. So the square root of t plus 1 equals 1 over x. Square it. So t plus 1 equals 1 over x squared. And then subtract 1. So t equals 1 over x squared minus 1. I'm going to take that and plug that into y. So y equals 1 over x squared minus 1 over 1 over x squared minus 1 plus 1. And that denominator, the minus 1 and the plus 1 will cancel, so I get y equals 1 over x squared minus 1 over 1 over x squared. If I just treat this as multiplication, it'll move up to the numerator. That'll be x squared over x squared, which is 1, minus x squared. Now, what does t being greater than -1 do? It makes x positive, which means that actually x has to be greater than 0. X is, since the numerator and the denominator are positive. But we know how to graph this much better than even plugging in points and making a table there. So what does 1 minus x squared look like? It's a downward facing parabola. But if we're restricted to x greater than 0, it's only the right side of the downward facing parabola. That's what the shape would look like. So here's a question. How are we traveling on this parabola according to time? What's happening is time is increasing. As t gets bigger, the denominator of x gets bigger, which means x is actually getting smaller. So we're actually traveling up this half of the parabola, which is kind of crazy as an idea. It's a half parabola and we're traveling up it, because as t goes to infinity, x gets 1 over a bigger and bigger number and gets close to 0. And as t goes to infinity here, y gets closer and closer to 1, but never gets there. This circle should be open because x is technically greater than 0 instead of closed. I just plotted it there. But it should be an open circle. So this is an interesting half parabola that you can graph using parametrics. By getting rid of the parameter, you just need to restrict the domain and then take into account the direction you'd actually be traveling. Now, the next one on page 3 is also interesting in that regard. It says cosine theta equals x over 3 and sine theta equals y over 4. This one's hard because it's going to be kind of hard to solve for theta, so sometimes you have to use other skills. In particular, cosine squared theta plus sine squared theta equals 1. Now what do we know cosine theta is? This is x over 3 and it's squared. Sine theta is y over 4 squared equals 1. Now this is x squared over 9 plus y squared over 16 equals 1. Since we just did this section last time, you should be able to identify this as an ellipse. The ellipse has a center of 0, 0, because there's nothing added or subtracted from y. In the x direction, it goes out the square root of 9, which is 3. In the y direction, it goes out the square root of 16, which is 4 on either side. If we're graphing it, this is an ellipse. Now, since it doesn't say anything about theta, there's no real way for us to know which way it's traveling. But we do know that generally theta makes a circle between 0 and 2 pi. So if we wanted to know the direction, we could say, well, what happens between 0 and 2 pi? Well, at 0, when theta is 0, cosine is 1, and if cosine is 1, that would make x 3, so we're at the point 3, 0. So we're basically traveling the unit circle direction as we go, without a restriction. We're traveling around the ellipse in that way if we want to know. Since it didn't restrict theta. In theory, that means we're traveling around in that ellipse forever and ever, and we'll never get away from it. Now, one interesting thing is, since we're taking our parametric equations and turning them into rectangular, we can go the other way. Something interesting that happens, though, is when you go from a rectangular equation to parametric equations, those equations aren't unique. So we'll demonstrate this by doing A, which is t equals x, and B equals t equals negative 3x. We're turning in 1 minus x squared, that same parabola, downward facing one we had from the first problem, and we're turning it into separate parametric equations. Now we already saw one set of parametric equations up here. Now let's see another one. So this first one is easy. It says if x equals t, what is y going to equal? Well, we just substitute t in for x. So y equals 1 minus t squared, which is just 1 minus t squared. These two, also make a set of parametric equations that draws the same picture. If I were to restrict t to greater than negative 1, I would get the exact same thing I got picture-wise on number 2. The only difference is I would have to restrict t, yeah, so I would be going the other way. Because as t increases, time increases, x would actually increase, which means I would have to be going to the right for x. And as t increases here, y would be going down. So I would have the same picture, but be going in an opposite direction than I was in number 2. Yet it's the same shape with two entirely different equations. It's kind of fascinating in that way. Now let's see t equals negative 3x just to see what happens. That means x equals negative t over 3 by dividing by negative 3. And I can again plug that in for y. Y equals 1 minus negative t over 3 squared, which is 1 minus t squared over 9. Okay, so again, these are two parametric equations. They make the same shape as part A and even number 2 from earlier. But this one, look, as t increases, x is actually going down, you would think. But x here is always going to be negative as time is positive. So what does that mean? That means if my time were restricted to greater than negative 1, instead of making the right side of the parabola here, I would actually be making the left side of the parabola, just with a different. So this is, even though they all would make the same shape without restrictions, all of a sudden the way your restrictions work, it changes the shape, the part of it that you're traveling on, and the direction. So it's kind of interesting in that way. So if I were to restrict the same way I restricted number 2, if t was greater than negative 1 here, it would be the part of the parabola greater than negative 1. So it would start basically here, and it would be going this way. So it's similar to the picture in number 2, except we have a slight extra piece and it's traveling to the right instead of left. If I did a restriction of t greater than negative 1 here, then what happens is, since x would have to be greater than negative 1, x would be less than 1/3. So we'd start about here, and I would have this half of the parabola, and I would be traveling this way. So this is why our parametric equations produce the same thing overall, but different restrictions affect different parametric equations entirely differently. Now you can read page 4 and 5 if you want. They're kind of interesting, but this is all the math on 10.2.